So in this video, I want to talk about how we can deal with discontinuities in an algebraic way. So imagine that you have this function f of x, which is this here, x squared plus 2x plus 1 over x plus 1. Now, if we plot this, we get a straight line. And yet, you cannot evaluate this function at -1 because you would get 0 in the denominator. Yet the limit exists at -1 and is equal to, in this case, 0. That's kind of an accident, but in any case, we cannot evaluate the function at -1, but we can find the limit. And graphically, the answer is obvious, but what if we didn't have access to the graph? How could we still see that the limit at x is -1 is equal to 0? Well, this function on top factors into x plus 1 times x plus 1. So if we were to get that, we would be looking at x plus 1 squared. I'll just write it this way. I'm not actually going to use it in the program, otherwise I'd have to use the double star. But in any case, so this is the same function. And if we cancel a factor of x plus 1, then it just turns into this. And that's a continuous function. We can plug into that and plug in -1. And when we do, we get 0. So that's how you can algebraically simplify something. And the only reason you're allowed to factor and cancel is because we're looking at the limit. And therefore, the x value is never equal to -1. So because the x value is never equal to -1, then we know this is not 0, and therefore it is legitimate to divide and cancel a factor of x plus 1. So while you cannot plug into the function, you can factor, cancel, and find the limit. And after you cancel, you can plug in. And that's generally how we solve algebraic sorts of limit problems. So for instance, if we are looking for the limit as x approaches 1 in this example, then we could take the numerator and factor it, and it becomes x minus 1 squared underneath the square root. Now, in the denominator, I'm also going to do a trick that I sometimes use, which is rooting the square, I'll call it, right? I don't think I've heard anybody else call it that, but I'll call it that because what I do is I square it and then square root it. That's a way that you can sometimes combine things that do and do not have a square root. So since the numerator has a square root, I would like to give the denominator a square root as well. And so I give it a square root, but to compensate, I also have to square it. Now, by doing that, in the numerator, I have exactly the same expression as I have in the denominator, and therefore they cancel, again, because I am not picking values exactly equal to 1, so there's no worry about the denominator being 0. I can cancel these factors, and they become just 1, so the limit is 1. So if you've never seen this technique of square rooting the square, just know that it's actually going to become much more important, especially as we move on to other sorts of limits. This will be sort of one of the official tools that you need to have in your toolbox for calculating limits. So let's now move on to another example of algebraically calculating limits. And as always, we have something that is discontinuous. We would like to have some kind of a factorization, something like it, so that we can cancel the x minus 1, and then after being able to cancel the x minus 1, we will be allowed to just plug in. So how do we cancel the x minus 1? It's not obvious in this problem. So the answer turns out to be something that you may not be familiar with, or if you are, then you may have forgotten it. But it's called the conjugate. So I'm going to use the conjugate of the numerator. I'd like to be able to square this, but I can't just square it. That would change the value. And if I multiply top and bottom by, say, square root x minus 1, that's a legitimate move. I can multiply the top and bottom by anything I want. But the problem with that is that after distribution, you can check for yourself. You can multiply that out and you'll get these obnoxious middle terms that still have a square root in them and cancellations do not come easily. That's the point of the conjugate. If I multiply by the conjugate of this, which is square root x plus 1, that's just taking one of the terms and flipping the sign, right? So it really just is what it looks like, flipping the negative to a positive in between. The point of doing that is after multiplication, and you should do this by hand if it's not immediately obvious, multiply these two numerators out, and you should get that square root x times square root x is x. The middle term should cancel, and the final term would be minus 1 times 1 is ultimately minus 1. So that's the point of the conjugate, is that the middle terms always cancel. And having done that, well, I multiply the top and I get this. I multiply the bottoms, and in fact, I don't even really do much about multiplying the bottoms, except that I just write them multiplied next to each other. And the reason I leave it like that is because I can see that a cancellation is coming, and that's exactly what I wanted. So when I cancel the x minus 1s, only 1 is left on top. Square root x plus 1 is left on bottom. This is now continuous at 1, so I just plug in and I get 2. This is generally how you find limits algebraically.